sorry, is your delta L, your change in L, right? So we assume, we make assumption, we assume, okay, this assumption is to make our calculation easier. Okay, I repeat again, this assumption is to make our calculation easier. So we assume that material 1 and material number 2 have the same change in length. Okay, we simplify it, we make that assumption. Okay, so I'll declare the pink one is the deformation Hey, Eugene, come on, ping. Deformation during loading. Okay, right? So we assume that delta L, right? We assume delta L is the same. Okay, we assume delta L is the same. So now when we go back to Hooke's law, okay, so we go back to Hooke's law. So Hooke's law, right, states that the stress is equal to Young's modulus multiplied by strain. Okay, so if we draw, what does this actually means? So if we draw a stress strain curve, all right, it basically, so the function stress is E multiplied by strain. Okay, so this is our Young's modulus. Okay, this is our E. Over here, this is our strain, and this strain we acquire from delta L divided by L original. Okay, so now knowing that, so this is a function of the line, yes, you agree, right? The y-intercept is equal to 0. That's the function of the line. Okay, so now we can write two equations. Okay, we can write two equations, so we can express that material number 1, so stress 1 is equal to Young's modulus of material number 1 epsilon 1. Okay, so this is our equation number 1. Okay, and then equation number 2, this is for material 2, E2 epsilon 2. So this is our equation 2. But remember, we make this assumption, right? We make this assumption that material 1 and material 2 have the same what? Delta L. Okay, we declare this assumption over here. So when that's the case, right? If delta L is the same, right? So we know that epsilon 1 will be equal to what? Epsilon 2. Okay, and again, I write down, we assume that delta L for material 1 and 2 are the same. Okay, right? So when that is the case, if we look at equation 1 and 2, right? So what we're going to do is we're going to equate. Okay, we're going to equate equation 1 and 2 with the above assumption. Okay, so we're going to make the above assumption, right, that the delta L is the same. So when is the case, okay, I'm going to write the formula or continue over the other side, because I think it's important that you all compare what's going on. All right, so what we have is stress 1 over E1, right, is equal to stress 2 over E2. Okay, and this is my equation number 3. Right. Okay. So that's our equation number 3. So we know, right? So what we know is that the load is equal to stress multiplied by area. Okay. That is the load is equal to, is basically force is equal to stress multiplied by area. Okay. So therefore, if we go look at this diagram, if we go look at px over here, right? Px are acting over two areas, right? So you have this area over here, right? This area over here, right? This area over here. This is your area 1. This area over here, that is your area 2. So both of them are absorbing the load or carrying the load. So we can write this expression, okay? Because it's sandwich material, we can write up that Px is equal to stress 1 multiplied by area 1. So this is carried by material 1, then plus by stress 2 area 2. Okay, so I'm going to call this our equation number 4, right? So we're going to let, okay, so there are too many variables now. Okay, we're going to simplify it. Okay, so we're going to let stress 2, right? So from equation number 3, okay, so from equation number 3, right, from equation number 3, we know that stress 2 is equal to E2 over E1 multiplied by stress 1. Okay, so this is our equation number 5. So now we are going to substitute. Okay, we're going to substitute equation number 5, okay, into equation number 4, right? So we will substitute that. Right, so we have Px is equal to stress 1 A1 plus by stress 2 is equal to E2 over E1, right? Stress 1 multiplied by A2. Okay, so we can bring out the stress 1. So Px is equal to stress 1 A1 plus by E2 over E1 A2. Okay, so from here we immediately can find our stresses for material number 1 is equal to Px divided by A1 plus by E2 over E1 A2. Okay, so this is the formula. Okay, so we just derive axial loading stresses for a sandwich material. So this and this expression are the same. Okay, but we made a simplification. The simplification we make is material 1 and material 2 have the same delta L. Okay, just a assumption. Okay, right? Okay, so now you can see that sandwich material under axial loading and bending moment, the formula is not exactly the same, right? It's not like Eugene. Why not we just put a n down here, Px over A. We can't do that. Okay. Okay, it's not that simple. Okay, now in bending moment we could do it, and I'm gonna tell you what is going on when we put a n, or when we put a n coefficient down here, right? How come it will work? Okay, so what are we doing down here, right? Now let me try to explain this n coefficient. Okay, so I'm going to go into how does N work for bending moment analysis? Okay, so for this case, we are going to focus on centric loading. I mean, centric or eccentric, the only difference is the axial loading. But okay, the axial loading for eccentric sandwich material is small, right? We just spend like 15 minutes to derive it. So we're going to focus on, okay, either way, the bending moment equation, what does it actually mean, either in centric or eccentric? The only difference in eccentric, you have the px to consider. Okay, so we're going to look at the bending moment now. Okay, so now if we have a structure now, okay, so I'm going to draw our this from here on. What we draw is the cross sectional view. Okay, I declare this. This is a cross sectional view. Okay, I'm emphasizing. So if I were to draw our transformation, this is our y, this is our z, this is the rotation in x. Okay, so cross section. So let's say if we have a material, okay, so we have a material like this. Okay, so I'm going to divide this. So this is steel. The top layer is made of steel. The center layer is made of brass. Hey, come on, Eugene. Center layer is made of brass. And over here is made of steel. Okay. So the moment that the moment for all these cases, the moment is applied about the z-axis. Okay. So what we want to find is IZZ, right? So we want to find IZZ, or we want to find moment. If it's moment about the z-axis, okay, we have to find IZZ. Okay. So if it's a single material, we know that we use stress x is equal to mz over izz multiplied by y. Okay, but we have a sandwich material. So for case number one, okay, so this is the original configuration. Okay, so case number one. Okay, so I'm going to call case number one. I'm going to call I'm going to declare that steel is the reference material. Okay, steel is the reference material. So we have to form, right, this equation, which is N of steel. Hold on, I'm going to bring this down slightly. Right. So we're going to use the reference material. So N of steel, right, is equal to Young's modulus of steel divided by Young's modulus of steel. Okay, steel, all of a sudden I cannot spell, right? So why divide by steel? Because we make the reference material steel. Okay, so this is equal to 1, right? Nothing changed, right? Now we have the end of brass